We left off in our last video talking about what's probably the most important sugar in this chapter, maybe one of the most important molecules we'll learn about in this course. It's an aldohexose called D-glucose, and it's so important for your health, for nutrition, for physiology, pathophysiology, and it's something I really want you to know and know well. This 6-carbon sugar with an aldehyde, as we noted before, has 4 chiral carbons. What that means is each one of those can be changed and in the opposite configuration. And that means we have 16 different types of aldohexoses that we can actually have, different isomers of glucose. In order to work with sugars like this, scientists came up with an alternative structural way to show it. As you can see in the structure we have right here, we've laid out these 6 carbons flat on the page, but then we have the OHs and Hs wedging out at you as if they're coming out of the page toward you. That's a little silly because we can't really do that in 2 dimensions, but nonetheless, that's how we often think about sugars like this. Scientists came up with a quick shorthand called a Fischer projection, and what that is simply this. We take a vertical line to represent the carbons. We go ahead and add in what's attached to the first and last carbon, in this case an aldehyde and a primary alcohol, aldehyde here, primary alcohol here, and we make horizontal lines for the OHs and Hs. And we're just going to assume that these are wedges coming out of the page at us, and we're just going to have that be sort of the default mode. At this point, what we can say about D-glucose is that the first chiral carbon's OH is on the right, the second one is on the left, the third and fourth are on the right as well. So sometimes when I think about D-glucose, which we abbreviate DGLC, I think right, left, right, right, after we've put on the first and 6 carbons outside of those. So this Fischer projection is very useful for us, and what it does is it allows us to draw out structures very quickly. At this point, I'd like you to pause for a moment, and I'd like you to look at the sugar right over here, which is not D-glucose. It's a different sugar. In fact, it's an important one in our body, not as important as D-glucose, but it is found in our body and found in our diet. And I'd like you to say what's different about this sugar and this sugar. How has it been chemically changed? Pause for a moment and we'll return and review it. Okay, I hope that you took some time to really think that through. It's very useful to engage yourself in these kind of things. I would note, first of all, what's not changed. This is still a 6-carbon aldehyde sugar. That is, it's an aldohexose. The numbering hasn't changed. What has changed, however, is the positions of all the chiral carbons. What was right, left, right, right is now left, right, left, left. And in summary, we've taken every chiral carbon, all 4 of them, 2, 3, 4, and 5, and we've reversed the chirality of each one of those. Technically, that's a mirror image. And a mirror image is also called an enantiomer. And this is an enantiomer pair. And enantiomers are going to be referred to as D-glucose and L-glucose, or L-glic. So, from now on, anytime we learn a sugar in the D form, such as D-glucose or anything else, we learn 2, because once you know a particular sugar in the D form, you can know it in the L form simply by switching the directionality of the OHs attached to all chiral carbons in that sugar. So we get 2 for the price of 1, and that's again going to help us build diversity. One last thing about this though, notice that we call this a mirror image, but the carbonyl is still pointing to the right. and the CH2OH is also pointing to the right. Well, keep in mind the first and sixth carbon are not chiral, and that means it doesn't matter which way they're pointing. So we could draw it either way and it would be correct. Keep in mind it's like the carbonyl up there is like a helicopter blade. It can be rotating around and we can draw it in any way we want and it's going to be okay. So that's enantiomer pairs, and that's a useful way to build sugar diversity. In our next video, we're going to be looking at more types of isomerization of sugars.